All right, so one question you might be asking when you're talking about phase changes and you're going from a liquid or a solid to a liquid to a gas, and you're like, well, if you watch the phase change diagram video, I really recommend that. But the idea is, I mentioned that, like, for example, chocolate has a different melting point than water, and a different melting point for, oil, and why is all that? Okay, so the main idea is there's an attraction, and I mentioned that in the phase change diagram. You're breaking attractions, and depending on how strong the attractions are between those compounds, that's going to determine the melting point and the boiling point. So let's just look at a couple. All right. So let's look at one that's a gas at room temperature, like oxygen. Okay. So we're going to compare oxygen. We're going to compare that to, let's compare that to water, because water, we all know, is a liquid at room temperature. And let's compare that to maybe salt, because salt is a solid at room temperature. So you ever think about that? I think it's kind of fascinating to actually think, why the heck do we have oxygen, water, and salt at different phases at the same exact temperature? So let's look at the molecules themselves and see what they look like. So oxygen is one oxygen bonded to another oxygen. Okay? So it's O2. Okay? So oxygen bonded to another oxygen. Water is H2O. And I've drawn this before. You have oxygen here bonded to a hydrogen. Okay? And salt, which is NaCl, is simply just Na bonded to a Cl. Okay? Now, the whole idea you got to remember is melting and boiling points isn't separating the elements. Okay? This water molecule is attracted to another water molecule. Okay? So I'm going to draw a bunch of these. So we got oxygen, and we got hydrogen, hydrogen. And why is there an attraction here? So there's an attraction right there. Why is there an attraction? Well, if you looked at the other video that I had on like how you are going to separate matter, you might notice that I mentioned that electrons get shifted. Oxygen likes electrons, and electrons are negative. So you have a negative side, and you have a positive side. So obviously another water molecule is going to be opposites attract. They're going to be attracted to the positive side on the oxygen. On the hydrogen is going to be attracted to the oxygen side because it's negative. And I think you kind of see that I could do this for a while though, and that's why this is what you would see whenever you're looking at a water molecule. If you're looking at water itself, millions and millions of these are all attracted. So the squiggly line means attraction. So I'll do another one. So another oxygen could be right here, bonded, and you have a negative positive there. I could draw another one. I mean, I'm hoping that you kind of get the idea that there's an attraction there. So it's not a bond. A bond means you have to take a ton of energy to break it. This is an attraction. So you can break it by adding heat. Okay? So there's an attraction there. Okay? Oxygen doesn't have a negative side on one because they're the same. So oxygen has evenly distribution of electrons. So there really isn't much of a negative and positive side. So if I take another oxygen, there's a very, very loose connection. So this is a weak attraction, okay, right there. Because there isn't much of a negative and a positive side. Here, there's a pretty strong connection. I would say, we can say medium strong. We'll say medium strong. Okay? And then over here, though, you have a very shifting of electrons. Okay? You got a chlorine really likes electrons, and sodium's kind of like, I do not like them at all. So you got a huge charge difference here. So when you have another NaCl, and you got a positive, negative, that's a strong attraction, okay? Weak, medium, strong, okay? So I'll kind of point it over in that direction there, all right? So the whole idea now is, do you have to know the names of these attractions? No, but it's nice to kind of figure this out. So these weak attractions are called London dispersion forces. So London dispersion forces are very, very weak. They don't bond, they don't attract those oxygen molecules very well, and we'll talk about why that relates to melting and boiling points. Here, these are called hydrogen bonds. So I'll just kind of put it, I guess I'll put it right here. H bonds we call it, hydrogen bonds. Okay? So I know, I hate to say hydrogen bonds because it's not a bond, it's an attraction. So whoever thought of the name didn't really think about it, but it's not, so these medium strong attractions are not bonds, but they're called hydrogen bonds. So there you go. Over here, this is a really strong, because this is ionic, this is an ionic bond where electrons get shifted really far on one side. So you have an ion, it's called an ion-ion force here, okay? So that's what makes that really strong, because that's an ion. An ion means it's a charge, so negative and positive. So you have a very strong attraction here, a medium attraction here, and a weak attraction here. Now I hope you can see that why oxygen is a gas at room temperature. It's so weak they don't stick. They don't stick at room temperature. They're moving around so much that they bounce and they're just there. Water, on the other hand, is kind of attractive, so they're going to hit each other, but they're going to be in a range of stickiness where they're going to be a liquid. And then when you have salt, they're so strong, they're going to be really close together. So you got to add a lot of heat here. So you got to add a lot of heat to melt. Okay? Here, you have to add some heat, so I'll just put it right here. Add some heat to be a gas. Okay? To boil water, you need to add some heat because you got to break these attractions. To melt salt, you would have to break these attractions here and make it looser so they would become a liquid. Here, you don't have to add, I mean, there's very little heat, very little. In fact, you can look up the boiling point or the melting point of oxygen. It's really low. For example, I mean, all the gases that are around us are really, you have to get them really, really close together to start sticking. So that means to get them close together, you have to have them stop moving, meaning lower the temperature. So if you ever saw Terminator 2, I believe, where nitrogen liquid was thrown over on the bad guy, he froze, right? Because liquid nitrogen is really, really cold because nitrogen will not become a liquid unless it gets really, almost stops moving to get them to stick. Otherwise, they're moving so much they're bouncing off each other. So to get the temperature to drop is the only way to get them to stick together. So at room temperature, that's so much heat and so much energy, that's plenty of energy to get these guys to become a gas. So that's why we have a gas here, and over here we have a liquid, and then we have a solid. All at the same temperature. All at the same temperature. We'll just say room temperature, right? So you've experienced that. So that kind of gives you an idea of the reasoning behind it. It's the attraction between the molecules themselves. The attraction between the NaCl and another NaCl. The attraction of H2O and another H2O. And the attraction of the O2 and another O2. Not the bond between them. Not the bond between them. Between the elements. Okay? It's the actual attraction between the molecules themselves. So there you go. Hopefully that helps.